So this is lesson 2.2, which is all about time, and we'll be covering several topics. So firstly, we'll talk about measuring time, so the whole issue of calendars. Then I'll talk about grasping time, by which I mean getting a feel for the timescales we might be talking about. Then we'll cover a method of measuring time in terms of human generations. Then we'll cover fractal time, which refers to the idea that short-term historical processes have a similar appearance to longer-term historical processes. And then we'll cover the idea of historical time, which is about measuring historical processes not in terms of chronological time, but in terms of the amount of human creativity that has occurred in a certain span of time. And lastly, we'll deal with two-dimensional time, which is about the idea that we experience time in two different ways. So let's start with calendars. As theoretical historians, we need to know when events occurred, and a calendar is a way of assigning each day a unique identifier. And it's usually based on a cycle, usually connected to some kind of astronomical rhythm. And we can have solar calendars that try to keep in sync with the solar year, which is 365 and a quarter days. That's the time it takes for the sun to return to the same position in the sky. And then there are lunar calendars, which attempt to keep in sync with the month of 29 and a half days. And then there are lunar solar calendars, which attempt to do both. And then there can be calendars based not on astronomical rhythms, but based on counts. So an example is a Chinese calendar that uses two counts of 10 and 12 days. So the first day of the cycle is day 1, 1, and that's followed by day 2, 2, 3, 3, and so on, up to 10, 10. And then the 10-day cycle starts again. So that becomes 1, whereas the 12-day cycle continues on to day 11. So the next day is 1, 11, then 2, 12, then 3, 1. The 12 count now goes back to 1, and then 4, 2, 5, 3, and so on. And this cycle repeats after 60 days. Now, the problem with these cycles is that they aren't a whole number of days, but we can only count in whole numbers of days. So if we want to say, the cycle repeats on a particular day, let's say after 365 days, actually it's 365 and a quarter. So we're going to be a quarter of a day out. And let's see how that works by drawing a timeline here. So supposing we start here and we call that the 25th of December in this year, and that's at noon. Then if we're trying to keep in sync with this, we have a calendar that's 365 days long, it repeats after 365 days. Then we'll count forward 365 days and we'll say that this is now the 25th of December again, and also that's noon. But the problem is that in fact the true year won't actually end until 6 p.m, a quarter of a day later. on the 25th of December. So we're a quarter of a day out. And then we count forward another 365 days to noon on the 25th of December. But the year now won't actually end until midnight on the 25th of December, because it's 365 and a quarter, and we're already a quarter out, so we're now 2 quarters out, half a day out. And then the next year we count forward 365 days again to noon on the 25th of December, and a full year, the sun won't actually have returned to the same position in the sky until 6 a.m. on the 26th of December. And then a year further on, we're here at noon on the 25th of December again, but the sun will actually be in the same position as it was then, now another quarter of a day later, which is noon on the 26th of December. So we've lost a whole day. We've got a day out of sync now. We're calling the 25th of December the same day. It should be the sun is in the same position, but actually it won't be in the same position for another day. So what we can do about that is add an extra day somewhere in here, a leap day. And that means we skip a day. So we don't count it in the normal cycle. And that means because we've skipped that day, we're a day short here. So this will actually be, we will now be counting this as the 24th of December. Because obviously in the Western calendar, our leap day is the 29th of February, which we don't normally have. So we kind of absorbed a day into the 29th of December. So we now only got up to the 24th of December here. And so this will be noon on the 25th of December. And that will be correct. Noon on the 25th of December, and noon on the 25th of December is when the sun is back in the same position. Now, many different calendars have been devised and been in use over the centuries and are still in use today. The Western calendar is a solar calendar, so it means that there's no relation between the months and the movements of the moon. Full moon can occur on any day of the month. It's all over the place. Now, knowing where a day occurs in the cycle is one thing, but it's no good just saying something happened, say, on the 5th of October. We need to know what year it is, so we need a count of years, and that means we need a year one, and that choice of a year one is known as an epoch. And when you combine a calendar plus an epoch, a year one, that is an era. So in the West we can say we have the Christian era because it's dated, our epoch is the birth of Christ. So in the Western Christian era, this is the year 2024. But in the Islamic era, which counts its year one as the flight of Muhammad to Medina, this is actually year 1446, for example. Now, I'll say a bit more about the Dionysian era, which is the era we use in the West. I just called it the Christian era, but we could call it also the Dionysian era, after the person who came up with the idea, Dionysius Exiguus, in the 6th century. So before Dionysius, years were referred to in terms usually of regnal dates. So we might say something happened in the 10th year of King Clovis. Or also years were measured in terms of the Roman consuls. So in Rome, each year 2 people were appointed as consuls. And so we might say something happened in the year when Brutus and Maximus were consul, for example. And that wasn't very convenient because you needed a list of who the consuls were in each year, or who the kings were and when they came to the throne, in order to kind of work out when things occurred and what the relationship between them was. So you can imagine that if we still use that system, something like the American Declaration of Independence, we would say, oh, well, that was in the 16th year of George III. And the outbreak of the American Civil War was in the, I think, the 24th year of Queen Victoria. Well, that doesn't give us a feel for what the relationship between them was. Was one before or after the other, and how much time elapsed between the two. So it's obviously much better to count, to say one thing happened in 1776 and the other happened in 1861. We've got a much better idea of what the historical relationship between them was. So Dionysius said, instead of counting in terms of the reigns of kings, we'll count in terms of the reign of Christ, who will reign forever. So we don't need to start counting over again. So he calculated he started with his year 1, the first year of the reign of Christ, when Christ was incarnated or born. Now it's thought that he kind of got that wrong a bit, but it doesn't really matter. It's just an arbitrary date ultimately. So that was year 1, and we just count forward from there. So we're still in the reign of Christ. So when we say this is a year 2024, we mean it's year 2024 of the reign of Christ. And the way Dionysius expressed it was, he said, it's in the year of our Lord such and such, and the Latin for that is Anno Domini, in the year of our Lord. So we write AD, Anno Domini 2024, and you can see from that the AD logically comes before the year. It's in the year of our Lord such and such. And the plaque that was left behind on the moon for the first lunar landing in 1969 said, put the date July 1969 AD. And the person who designed the plaque later realized, and he'd made a boo-boo there. He should have put the AD beforehand, at least as far as pedants were concerned. So he kind of regretted that he'd made such a grammatical error on the one of the most significant plaques that's ever been created by humans. Now, in the 17th century, people were thinking about much longer historical periods, and they thought, well, what do we do about dates that occur before the incarnation of Christ? And so they came up with the concept of before Christ, and so we have BC dates. Now the problem with that is that we don't have a year 0. So we start with AD 1 and so on. We then have 1 BC here and so on. There's no year 0, and this is a bit of a problem for theoretical historians who want to treat these things mathematically. You're drawing a timeline. You don't go straight from +1 to -1. You should have a 0 in the middle. Now, how we deal with that is basically just ignore it for most of the time, because the kinds of things we're talking about, we're not really interested in exact dates anyway. We're talking hundreds, thousands of years, so it's not really an issue. But it's something to bear in mind. Now, of course, not everyone considers Christ their king, their Lord. So some people, rather than say in the year of our Lord AD, prefer to use the term the common era. So the common era is the era in common use, which is the Western Christian era, but instead of saying in the year of our Lord, just say this is 2024 of the Common Era, and that gives us also before the Common Era, the BC dates. And archaeologists, when they dig something up from the ground, it doesn't come with a date stamp usually, but what they do know is how old it is. So it's 1,000 years old. So archaeologists also use the term before present, BP. So if it's 1,000 years old, then it was created 1000 BP. Now the problem with that is, of course, the present is constantly changing as we move through time. So there is an agreed archaeological present of 1950. So 1,000 before present means 1,000 years before 1950. Okay. Now moving on to the next topic, I sort of talk about grasping time. So it can be, difficult to get your head around some of the dates that we're talking about or might be talking about, especially when they're a long time in the past. So, if we might be told that civilization collapsed because it experienced volcanic eruptions, let's say in 1860 BC, and then again in 1650 BC. And it's difficult to sort of, as you gloss over that, it sounds like they're pretty close together and they're kind of occurred on top of each other. And you can say, oh, well, yes, they were having all these volcanic eruptions, no wonder the civilization collapsed. Or, we might be told that an early medieval king fought a battle against the Burgundians in, let's say, AD 537, and he fought another battle against them in 564. And again, it kind of seems like, well, he was always fighting these Burgundians, these battles occurred pretty close together. But I'm going to talk through 4 strategies that we can use to get a better mental feel for how these dates seemed like to the people at the time. So the first way is assimilate it or equate it to the 20th century. So with this king and his battles, the idea behind this is that most people have a reasonable feel for the different decades of the 20th century from watching films and so forth. We kind of get a feel for what the 1920s were like versus the 1940s and 1980s. So if we take this, we can say, well, 537, well, that was in 1937, that was in 37. So that's the time of the Depression era and the rise of Hitler. Whereas this battle occurred in 1964. So that's the time of the Beatles and the miniskirt. So with that way, we can get a feel for the kind of span of time that passed between these two events, as it would have seemed to people at the time. In other words, by the time you get to the miniskirts, the Depression era seems quite a long way in the past. And to this king, this battle was not, something immediately following on. An awful lot of water could have flowed under the bridge during that time to the people present at that time. What happened back then would have almost seemed like a very long time ago. Then another thing we can do, because assimilating to the 20th century isn't going to work for something like this, is to count back from today. So if we want to get a feel for the difference between those two times, we can start with a later one and say, well, that's now. So 1650 BC we'll take as, let's say, just for a round number, 2025, the year 2025. Then 1860 BC, that's 210 years beforehand. So will take us back, so that will be the equivalent of 1815 from our perspective. from there back to there is equivalent of from us today, 2025, back to 1815, the Battle of Waterloo. So, you know, that should give us a feel that for the people who experienced this, that volcanic eruption was an awful long time ago. There's nobody alive today who knows that time, and there's not even anybody alive today who knows somebody who was alive at that time. A third approach is to think in terms of the human lifespan. The author Geoffrey Bibby used this in a book about the Bronze Age. He took 1,000 years of Bronze Age history and he divided it up into 70-year chunks, taking the human lifespan to be 70 years. So with this, we can say, well, that 210 years, that's 3 human lifespans laid end to end. And a fourth way is to use 4-century blocks. So this is suggested by the author Charles Murray. The same way as, you know, most people have a feel for the different characters of the decades of the 20th century, most of us have a feel for the different characters of the centuries, the 20th century versus the 19th century versus the 18th century versus the 17th century. We have a feel for, you know, the kind of fashions that were in use, the kind of technologies that people had, the kind of events that were relevant to each of those centuries. So he says we can sort of picture what 4 centuries looks like, and we can then use that as a yardstick to measure historical time. So if we go back to, let's say, the beginnings of agriculture, 8,000 BC, which is 10,000 years ago, that's 25 of these blocks of time. So if we can sort of visualize what 4 centuries looks like, then it kind of gives us a feel for what that means. 8,000 BC is 25 of these units. So let's talk about measuring time in terms of generations. When I told a friend of mine a few years ago that I had developed a new dating system, he was at first quite interested. He thought it was going to help him with his Tinder matches, but then he realized that wasn't what I was talking about. Well, I think he was pulling my leg. But the idea here is that we start in 50,000 BC. And given the timescale we've adopted for theoretical history, that means that most of our dates are going to be positive. And we call this generation 0. So that avoids the no year 0 problem. It means that if we do have to go to negative times, it will still work mathematically. And we work in terms of generations of 25 years, which is a nice round number, and it means that there are 4 generations to 100 years, which makes it easier to convert the dates. So all the next 25 dates from 50,000 BC on are part of generation 0. So 49,999 BC, 49,998 BC, all the way up to 49,976 BC. That's all generation 0. And then 49,975 is the beginning of generation 1. And then the next 25 years are all generation 1 up to 49,950 BC, which is the beginning of generation 2. And if we want to identify individual years, we can do that by identifying which year they are in the 25-year block. So for 50,000 BC, that's generation 0, and it is year 0 of the block. And then The next year is G01. It's the first year. The second year, G02, all the way up to G024, and then this is G10, and then you've got G11 and so on, all the way up to G124, and then the next is G20. So we can identify individual years. And so if we take a particular date, let's go for the last glacial maximum, which we'll say was 18,000 BC. We can convert that into a generational date by saying, well, 18,000 BC that's 32,000 years on from 50,000 BC, and so that's 320 centuries, and we said there are 4 generations in a century, so that gives us 1280. So the last glacial maximum was generation 1280. And in the textbook I gave a table in which I put the certain historical events. I'll put it up here on the board. I put certain historical events and their conventional dates and then converted those into generational dates. Unfortunately, I made a few mistakes. I got 3 of them wrong, out by a year or so. So that's an exercise for the reader to check those over and find the mistakes. I've corrected them in this version of the table. So if we start back here, the beginning of the Upper Paleolithic, we just said that's generation 00. The last glacial maximum we've calculated is G1280. Agriculture, G1600. Then we can say the Pyramid of Cheops, the Great Pyramid, G1900. The end of the Western Roman Empire comes out at 2019. The Columbus's first voyage comes out as 2059, G2059. And then today, if we're in 2024, that's 2080. We're in generation 2080. And the point of this is that it makes the dates more manageable. So we get a kind of better feel for the relative timescales of things. So, you know, we can see that the invention of agriculture was in generation 1600. The Great Pyramid was in 1900. That's 300 generations later. And then we're only 180 generations beyond the Great Pyramid. So we've got a feel for what those timescales are, which is, you know, much easier to grasp than when we're dealing with AD and BC dates, and also these thousands of years that are difficult to visualize. The numbers are more manageable here. And we can also measure spans of time in terms of generations. So we can say, which we can write as a letter G. So that's to measure a span of time. So, for example, we can say the whole of human history, looking at this table, if we're in G2080, that's the whole of human history is almost around about 2,000 generations. You know, it's 2080. It's 2000 G. And then if we go back to the Pyramid of Cheops, that's 1900. So compared to 2080 today, so the Great Pyramid is about 200 G ago. And then Columbus, we said, was 2059, and we're in 2080. So Columbus is about 20 G ago. And then, obviously, depending on how old you are, but you were probably born about 2 G ago. So we've got those relative timescales. We can see that your lifetime is about 1,000th of the 2000 G. And, you know, it's 1/10 of the time back to Columbus. Now, we can also use this generation concept to think about the relations between generations. So if you were born, let's say, in generation N, then your children are likely to be born in Gn+1, and your grandchildren are likely to be born in Gn+2, and your great-grandchildren will be born in Gn+3, and so on. Now, if you were born in Gn, you're likely to be still alive at this point, but by Gn+4, you're very likely to be dead. So that gives us an idea. If we know that somebody was born in a certain generation, it tells us what's plausible about their children and their great-grandchildren and how long they lived in terms of those generation times. We can sort of guesstimate. It also means that if we go over here, well, let's get rid of that. If you were born here in generation N, then we said that you will go on to Gn+1, Gn+2, Gn+3. Your lifetime will probably last into Gn+3, and conversely, people who are born in Gn-1, in Gn-2, and even in Gn-3, those people, back to then, most of them will still be alive when you're born. So as if you're born in Gn, you kind of span a 7-generation block of time, and you connect people from this Gn-3 up to Gn+3. And the annal historians point out that historical processes have different timescales. So politics, for example, has a timescale of a few years. That's how often we have an election. And then there's the human life cycle of about 70, 80 years. And then there are what they call the longue durée, the long duration, the long timescales, things that develop over the course of centuries or even a millennium. And given that history has these different timescales, it makes sense to use different rulers to measure it. If we're measuring distance and we're measuring things, around the home, we'll use a ruler. But if we're measuring the distance to the nearest town, it wouldn't make sense to use a ruler. We'd use a mileometer or something. So we need measuring instruments that are suited to the kinds of things we're trying to measure. And so this generation time dating scheme is kind of more suited to measuring the great spans of time that we might be talking about if we're talking about the time back to 50,000 BC. And it makes sense to use that rather than the ordinary calendar that's more suited for, remembering people's birthdays or something. Now, the next thing I said we'd talk about is fractal time, or I'll put up self-similarity. In history. So we've seen that big history curve, there's very slow development, and then it sort of takes off. And let's put in some of the milestones of big history. So we can say start back here, we've got stone tools. Then the invention of agriculture here, let's say, and then industrialization, and then cybernetics, computing. So these are kinds of stages in that big history evolution. But what we could do is home in on just the time up to stone tools. And if we did that, we'll plot just up to stone tools, we'll find that we get a similar hyperbolic curve that looks like that, because we've got back here the first stone tools, which were kind of just pebbles, you know, roughly chipped like that. So that's just a pebble with a few bits knocked off it. And then later there came what they call the bifaces, which is where the whole stone was chipped away to make a kind of axe. And then the next stage in the evolution of stone tools was flakes, where here the people chipped away the flakes to get to the stone, which was what they used, whereas then here it was discovered that actually you can use the flakes, which are nice and sharp. And then later on still came blade technologies, blade-based stone tools, which are specifically struck to be nice sharp blades. And so the point is that in the evolution of stone tools, these new stages came at an accelerating rate. And so we get that same kind of takeoff appearance. You know, these tools were used for millions of years, then hundreds of thousands, then a few thousands, and then centuries, and we're away with the flakes. And in the book I showed another example of that in terms of British industrial production. The output of British industry from, let's say here, 1200 to 2000. And somebody has made the effort to calculate that all the way back to then. And if we plot it, we get, are you familiar, hyperbolic curve. And we might say, looking at this, well, you know, here around 1800, it looks pretty flat up to there. So if we focused on 1800, surely we would get a sort of much flatter thing, or maybe something more like a straight line. But if we actually do that, I'll put IP, industrial production, and from here 1200 now only to 1800, we get that same kind of curve. And that is because what was happening in 1800 only looks small on this diagram because of how it is related to what's happening in the year 2000. But related to what was happening in 1200, it was much higher. So we do see that kind of takeoff again. And so what we can say here is that if we look on a long time scale or a short time scale, we get the same kind of appearance in these cases. So we could say these charts contain smaller versions of themselves within them. On the shorter time scale, they contain the same kind of shape as on the longer time scale. So this is what we mean by self-similarity. And in the book Deep History, the Architecture of Past and Present, in the chapter called Scale, the authors talk about this fact, and I think they use the term fractal, because the term fractal is used for things that contain smaller copies of themselves. So fractal and self-similarity mean much the same thing. And they point out that it always seems to be that these, what they call J curves, I've been calling hyperbolas, or some people call them hockey sticks. They point out that it always seems to be sort of in the last 200 years that things take off. Again there, it's always the last 200 years. And they've just noticed this in a lot of charts that are produced, whether it's about climate change or British industrial production or whatever it might be. it always seems to be, the charts always seems to show some kind of takeoff in the last 200 years. And that's because the timescales we were using and where these hyperbolic curves seem to turn the corner. Now I said that they use the term fractal for this, and the classic fractal is a fern. So a fern here is, well, I'll draw a fern, it's a stem with some branches off it, and then off those branches there are smaller branches, and off the smaller branches there are still smaller branches, and so on. So the big branch has smaller branches, the smaller branches have even smaller branches, and the even smaller branches have still smaller branches. It's self-similar. If we focus in on a small branch, it looks the same as the overall thing. Just the same as here. If we focus in on a small part of the chart, it looks the same as the overall chart. So these, we also say that, describe these as scale free, because whatever scale we're looking at, whether it's big or small on the fern, it looks the same. The appearance of it doesn't depend on the scale, it's scale free. So these terms are all kind of related: fractal, self-similar, scale free. And we'll see later on when we get to the mathematics part of the course that this is also related to what are known as power laws. Power laws have this property of being fractal, self-similar, scale-free. But as I say, we'll come on to that later on, but I just mention it for completeness now. And this fractal nature of history is also seen in society. So it's not just sort of temporally that human societies are self-similar, but we can also see it, for example, in institutions. So back in the Stone Age, you had individual families that were independently roaming the landscape, hunting for their food. Then later on, when villages emerged, later on as population grew, villages emerged. So you didn't just get a bigger family, you got villages that contained multiple families as the village. And then with the development of cities, a city is not just a big village. A city contains neighbourhoods, which are themselves villages containing families. The city. So we have a kind of fractal structure here, that the city contains smaller copies of itself, which contains families which are smaller things still within it. We also see this kind of fractal structure in the way population is distributed across the landscape. So we know that, we have the big city here, and that is surrounded by towns, and then the towns are surrounded by villages, and so on. So again, we've got a kind of self-similar pattern that if we zoom in, we see something surrounded by smaller things, or if we zoom out, we see something surrounded by smaller things. So these things, fractal, self-similarity, scale-free, and as we'll see, power laws, seem to be an important theme and principle in historical processes. The next thing I said we'd discuss is historical time, as opposed to just ordinary time. So we've seen these J curves of the speeding up of historical change, and we can understand that in terms of there being more people around, so more things happen. So back in the Stone Age, there was maybe 1 million people on Earth, whereas today there's almost 10 billion. So it's not surprising that things happen a lot faster, that because there's a lot more people to have ideas and do things, there's just a lot more human activity, or we could say a lot more human creativity. So the amount of human creativity that we would get in a year from 100 people is less than we would get from 1,000 people. And so to measure history, we should take into account not just the time that elapses, but also how many people there were to make things happen, to achieve creativity. So we might measure the historical processes not in terms of that elapsed time, but in terms of what we could call historical effort, which is a measure of the number of people multiplied by the time. So it would be measured in person years. So historical time can be calculated as the number of people, the population, multiplied by the time. So if there's 100 people in a year, they produce 100 person years of human creativity. If there's 1,000 people in a year, they produce 1,000 person years of creativity. Now, because population is itself changing with time, strictly speaking, we want to write that the historical time is the integral of population as a function of time with respect to time. That's the integral. Now, don't worry if you're not familiar with that. We will talk about some of these calculus ideas in the mathematical section. But what this means is that we're just taking the population at each year and then adding them up. So if we're, say, doing it for the 19th century, because the population was changing through the 19th century, we can't just multiply the population for the 19th century times 100 years for the 19th century, because the population, what population do we take? The population at the beginning of the 19th century was different at the end. Well, we could take an average, but to be more precise, what we do is we take it step by step. So we take the first year, the population in the first year, and that's one, whatever that was. And then the second year, we do that population multiplied by a year. And then the third year, the new population multiplied by a year. And then we add them all up. That's what this is basically saying. And then the amount of history that has happened to date is the cumulative amount of time. So it is this cumulative historical time. And we can kind of draw a chart of how historical time has varied with ordinary chronological time. And, not surprisingly, it looks something like this. Historical time has been increasing faster more recently with more people. Back then it increased slowly because there are very few people, but now with 1,000 more times more people than there were in the past, we've got 1,000 times faster that historical time is increasing with time. And we can compare a few historical periods that share the same amount of historical time, the same amount of human creativity. So let's see, I've got the period from 7,500 to 2,300 BC. That is equivalent to the time from 306 AD 306 to 630. And that in itself, or that in turn, is equivalent to the time from 1978 to 1989. These three periods all had the same amount of person years of history. So the amount of history in that period is equal to the amount of history in that period is equal to the amount of history in that period. So now we begin to see why things, happen a lot faster. Technology develops a lot faster. 11 years of the late 20th century is equivalent to almost 5,000 years of the Neolithic period. But in fact, what we find is that it isn't quite like that, even though strictly we should find these to be equal. Actually, change was happening faster in this earlier period than we might expect using this idea of historical time. And that suggests that people were more creative back then than they are today. So things developed a lot more slowly, but not as slowly as we might expect given the few people that were around. And that suggests that, well, one explanation for why we seem to be less creative today is that maybe with more people around, there's more duplication of effort. Again, we will come back to these things later in the course. We're just kind of skimming through, introducing us to some basic ideas at the moment. And then the last topic on time, as said, would be two-dimensional time. So we experience time in two ways. We live through time, and we're also changed by time. In other words, we grow older, we age. So let's plot a chart showing time here and age, the other dimension in which we experience time, along the vertical axis. And at a particular time, let's write for concreteness, this is 1920, we'll put here the year 2000. There were different ages at that time. So in 1920 there were some people who were 10 and some people who were 90 and all the different ages between. So we can draw those ages at each particular time. So that's the age level of 90, this is the age level of 10, etc. And then if we take a particular group of people who might have been children in the 1920s, as time goes on, they also age, so that by the year 2000, they end up here, let's say here in their 80s. So as time goes on, they're experiencing the passage of time itself, but they're also experiencing their own aging process. And these are the same people then, but they're in a different role in society. Here they're the children, here they're the older age bracket. And they kind of connect this time. The people who are in their 80s in the year 2000 connect the childhoods of 1920 and the experiences of being a child in 1920 to the year 2000, and also the experiences of being in their 40s in the 1960s. So they bring that experience. And that's really all I want to say about this at the moment, that idea of two-dimensional time. But it'll become important later on in the course when we come to talk about human generations and the idea of generational cycles.